Welcome to the third Watershed Council Icebreaker Speaker Series. I'm Katie Wolf. I'm the Executive Director of Tip of the Mitt Watershed Council. We're really excited to have so many people signed up today and hope that you will enjoy and learn a lot today. We have a phenomenal speaker. But before we get started, I'm going to go through just a few things. I just want to share with you, many of you are familiar with the Tip of the Mitt Watershed Council. We were founded in 1979. We're in our 44th year of serving as the voice for and protecting Northern Michigan's fresh waters. We cover 5 major watersheds in Northern Michigan. Those extend in 4 counties. And then obviously we reach into a few other counties as well. We're fortunate to have an abundant amount of freshwater resources from 2,500 miles of rivers and streams and thousands of acres of inland lakes, as well as the Great Lakes themselves. And so we are blessed with all of our fresh waters and work very hard to try to keep those clean. There's a few housekeeping details that I want to cover with you. All attendees will be muted throughout the webinar to avoid background noises. We do use the Q&A. If you have questions, we encourage you to post your questions in the Q&A box. We will not use the chat session for participants, but we will be posting links and things like that on our end in the chat box. So if you want to capture some of those, or if there's specific instructions to the audience, we'll post those in the chat box. We have a very full presentation today, and so we anticipate that there will be several questions. If by chance we don't get to your question, please go ahead and post it, and we will follow up with you and make sure you get an answer. And lastly, this webinar is being recorded and we will make it available the next day. If you go to our website for watershedcouncil.org past events, we will also post it on our YouTube channel and notify people through Facebook that it has been posted. So those are ways that you can, if you have friends you want to share it with, that would be great. So it is my absolute honor to introduce Knute Nadelhoffer today. He is a professor emeritus at the University of Michigan. If you follow climate change, you may be pretty familiar with him. He was in the Department of Ecology and Evolutionary Biology at the University of Michigan and is a fellow of the American Association of the Advancement of Science and the Ecological Society of America. He served as director of the University of Michigan Biological Station on Douglas Lake in Northern Michigan, a very important partner to the Tip of the Mitt Watershed Council. And then he retired in December 2020, but obviously still very, very active at the biological station. He was just mentioning he was there this weekend. He is an ecologist with expertise on forest and Arctic tundra ecosystems and their interactions with global climate system. He serves on the board of directors and the Science Advisory Council of the Environmental Law and Policy Center, a nonprofit organization that advocates for scientifically based environmental and energy policies in the Great Lakes region and Midwestern states. Dr. Nadelhoffer received his PhD from the University of Wisconsin-Madison in 1983. He was a research scientist at the Ecosystem Center in Woods Hole, Massachusetts, and also a Fulbright Research Fellow at the Norwegian Institute of Water Research. He was a guest professor at the University of Copenhagen and has served as the director of the National Science Foundation's Ecosystems Study Program from 2002 to 2003, and as president of the Association of Ecosystem Research Centers from 2005 to 2006. He served as an expert reviewer for the 4th assessment report of the Intergovernmental Panel on Climate Change. Many know that is IPCC, Climate Change 2007 Working Group on the impacts, adaptation, and vulnerability. The IPCC IPCC Special Report on Climate Change in Land in 2019 and the IPCC Sixth Assessment Report in 2021. He has published over 170 peer-reviewed journal articles, data sets, book chapters, and reports describing ecological processes at local through global scales. I was fortunate to first meet Knute in Chicago at a conference on shoreline protection for the Great Lakes, and knew then that we definitely wanted him as part of our Icebreaker series. I'd like to welcome Dr. Nadelhoffer, and I know you will really enjoy this presentation. Thank you. Dr. Nadelhoffer, if you could unmute.
I'm so sorry. I had to close out my presentation. And now I am set. Well, thank you very much, Katie, and thanks to the Tip of the Mitt Watershed Council. What an amazing organization Tip of the Mitt Watershed Council is, and I'm very happy to give this talk, and I'm honored to learn about what I've done. I didn't remember all that stuff, so what happens when you're retired. So today I want to talk about our emerging climate challenge and thank everyone for their tuning into this talk. I'm looking forward to your comments and questions at the end. I want to first start with some things to know about climate change. We're going to talk from the global level down to our regional level. This is a map that I'll show later, but this is the U.S. Drought Monitor. It's, I believe this is October of this year. You can go to the U.S. Drought Monitor and track droughts. You can see the Great Plains in the west, of course, have been in an extended, exceptionally severe drought, and many other parts of the country are in drought conditions as well. So some basic things to know about climate change. Climate change refers to long-term shifts in weather conditions. Day-to-day weather, like the thaw you had in northern Michigan just yesterday, is not climate, it's weather. And over most of Earth's history, natural processes have been responsible for periods of climate change. I often hear, well, everything's cyclical and the climate changes, it gets cold, it gets hot. That's true, it does. We understand the natural processes that drive those cycles, but now humans are responsible for climate change. Human activity is the main cause of recent climate change against a background of longer term changes that are dependent on things we understand. Accumulation of greenhouse gases, particularly carbon dioxide, methane, and nitrous oxide, due to the combustion of internal combustion engines and coal and oil and gas-fired power plants, and also agricultural practices, is unprecedented in human history. The evidence is based on physics, atmospheric chemistry, and intensive measurements of the Earth's surface temperature. The data produced by these measurements and these scientific projects are peer-reviewed, open to the public, and I'll try to summarize as best I can all those basic drivers of the climate. Human-caused climate change now leads to droughts, extreme weather events, ocean acidification, and more. Lake level variation, sea level rise, human health effects. In confronting our climate crisis, and it is a climate crisis, tending toward a climate catastrophe, frankly, It can improve our economies, it can protect human health, and contribute to a more just world. We can do good things as we address climate change. We know that the West has been burning. We know that we've had hurricanes at increasing frequencies and intensities. And Katie talked about the Intergovernmental Panel on Climate Change. People are often misunderstand what the IPCC does. The IPCC is not a scientific research organization. Rather, it summarizes the research of science all over the world, and it provides basic scientific assessments on climate change and its implications and future risks for policymakers, people who are elected to govern, people who are working in agencies to manage risks. The most recent assessment report, number 6, I reviewed parts of that. There were 234 authors, scientists from 66 countries who reviewed and synthesized over 14,000 peer-reviewed science papers. The draft report is reviewed by governments and experts, and 78,000 comments from 46 countries were solicited. Regional fact sheets and interactive atlas are available, and you can do a search engine search for IPCC and basically pull up all those documents. They are huge and long, but they have some nice summaries. The most recent IPCC report says, with increasing confidence since the first one, recent changes in climate are widespread, rapid, and intensifying, and they are unprecedented for thousands of years. We human beings are unequivocally responsible for global warming. Some systems are moving toward irreversibility and won't be able to come back to, quote, normal for centuries. Time is running out, but there is time to avoid the worst. I recently come to the conclusion that, we could have played offense 30, 35 years ago, knowing what we knew, but we did very little to forestall this. And now we're playing defense. We're basically doing damage control and hoping that we can reduce the emissions that are causing climate change quickly. The last decade was 1.1 degrees centigrade, almost 2 degrees Fahrenheit warmer than in pre-industrial time, let's say Civil War, American Civil War. We're likely to increase above pre-industrial temperature by 2040 by at least 1.5 degrees. And the damage that's being done now at 1.1 degrees C above pre-industrial temperatures is measurable and large. It will be larger and more severe if we exceed 1.5 degrees Celsius. CO2 is the highest that it's been in at least 2 million years, and probably for millions of years longer than that. CO2 is the main driver of global warming. Sea level is rising faster. Arctic sea ice is lower than at least 1,000 years. And we are experiencing extreme heat, drought, heavy rain, wildfires. Oceans are warming, acidifying, and losing oxygen, and sea levels are rising. More than 3 decades ago, in 1988, James Hansen testified before a Senate Energy Committee and alerted the country to global warming. He said global warming was already detectable and would grow far worse with time. And he was right. This is a graph produced by NOAA, the National Oceanic and Atmospheric Administration. I'll show lots of graphs. On the left side, we'll spend a little bit of time with this. On the left side is the anomaly in degrees C. The anomaly is the deviation in global temperature from an average period ranging from 1901 to 2000. So you can see a flat line here where annual global temperatures range above and below from about 1930 to about 1980. They're pretty much tracking the global mean, which is set at 0. But from about 1980 onward, the annual trend in both degrees Celsius and degrees Fahrenheit is steadily upward. It bounces around, but the temperature has increased at a level of about 0.2 degrees Celsius per decade. Predictions have come true with serious consequences for the planet. Since 1980, the globe has warmed by 3.4 degrees Fahrenheit, almost 2 degrees Celsius per century. That's the per century rate. Of course, we've only been about a half century since 1980, so cut those numbers in half for 1980 through the present. The US lower 48 states have warmed by 4.2 degrees Fahrenheit per century, and Michigan has warmed at a warmer rate than either the globe or the country at 4.8 degrees Fahrenheit per century. This is a map from NASA, a global heat map. You can go to the link down here and get maps like this for any month, year. This is a heat map. It shows high deviations from the 1951 to 1980 average, mostly in the Arctic, as much as 8.7 degrees Celsius for December 2022, just 2 months ago in the Arctic, and less warming in a relative sense as we get to the equator. But note that the average temperature is increasing, but there are places in December that were cooler. So temperature is not evenly distributed over the Earth in space and time, but on average, the temperature is increasing, putting more energy in the atmosphere to fuel storms and extreme weather events. Some global highlights, if we can call them that, from all this research as summarized by the National Oceanic and Atmospheric Administration at this link. The 2022, last year's average temperature across the land and ocean was 1.5 degrees Fahrenheit above the 20th century average. This was the 6th highest among all years in the 1880 to 2022 record. It was only about 1/4 degree Fahrenheit less than the record value set in 2016. Last year marked the 46th consecutive year since 1977 with a global land and ocean temperatures above the 20th century average. There are people in this seminar who have never seen an average global temperature year, who have not lived through one, if you're under 46 years old. The 10 warmest years on record have all occurred since 2010, and 9 of the last years are among the 10 warmest years on record. What's driving this? This is the longest running record of global carbon dioxide that's measured in the atmosphere at the top of the Mauna Loa Observatory in Hawaii on the Big Island. David Keeling in 1958 took his flasks to sample air to the top of Mauna Loa and set up a monitoring station to measure carbon dioxide. And what you see on the left is the parts per million of CO2 at the top of Mauna Loa, ranged in 1958. Well, let me just put the number up. It was 315 parts per million when he started measuring. And this last December, it was 419 parts per million CO2, which is about an increase of 1/3 over the 1958 level, which was already above the pre-industrial level of about 280 parts per million. Why does this matter? Well, let's look at the longer record of CO2 that we can get out of ice cores from Greenland and south in Antarctica. On the right, you see the CO2 concentration. You can see it's been as low in the past. This goes back 450,000 years, almost 500,000 years. It was 180 parts per million at its lowest, but it always ranged over the past 500,000 years, and now we know actually the past million years, between about 280 and about 180, bouncing around. If we look at the interglacial times, those 15 to 20,000 year periods where much of the ice in the northern hemisphere melts, we can see that those are the periods of time when CO2 concentrations are at their highest. And as the climate cools in the past, CO2 concentrations are lower. Now I'm going to overlay that curve we just saw, the Mauna Loa curve, which goes up now to 420 almost. That's the human footprint. That's what we've injected into the atmosphere, conducting a global experiment in climate. This is the graph I just showed on that time scale. So we have a time scale of about 58 years, 52 years, overlaying on a 500,000 year time scale. Not only has CO2 gone up, carbon dioxide, but other powerful greenhouse gases, methane and nitrous oxide, have all gone up. People talk about the hockey stick. Well, this is the hockey team. This is the hockey team that's driving our climate into a warmer world. Methane, of course, and nitrous oxide are both actually more powerful than carbon dioxide in terms of per unit impact on the climate. And those concentrations, however, are measured in parts per billion rather than parts per million, which is on the left-hand scale, against which carbon dioxide is plotted. On the right-hand scale, we plot in parts per billion, and that is nitrous oxide in black, methane in green. So why do these matter? Why do these increases in greenhouse gases matter? Well, let's think about the sun. The sun radiates shortwave radiation. That radiation we don't feel as heat until it enters our bodies or until it enters the earth, and re-radiates as long-wave infrared radiation. On the way to the Earth's surface, some of the solar radiation, the shortwave radiation, is reflected by clouds and atmospheric particles. Some reaches the Earth's surface and is reflected. If you went outside in northern Michigan last week when there was bright snow and sun shining, you might have had to wear sunglasses because the white snow reflects a lot of the shortwave radiation. But what happens is the radiation that's not reflected is it gets absorbed and gets re-radiated as infrared radiation, which is captured by our greenhouse gases that warms the atmosphere. In fact, this is how it works. This is a little graphic I worked on. This is a molecule of carbon dioxide, a representation. And when I press this button, a long-wave radiation, short-wave radiation is going to come in, bounce back as long-wave radiation, and excite that molecule of CO2. I'll do it one more time. Short-wave coming in, long-wave going out, exciting that atom or that molecule and causing heat. When these molecules vibrate, when their electrons are excited, they, by infrared radiation, they wiggle. They wiggle and cause heat. Even though they're less than 1% of the atmosphere, far less than 1% of the atmosphere, these are the only gases, a few other minor ones, that reflect and re-radiate heat, whereas oxygen and nitrogen in the atmosphere, because of their architecture and their shape, they don't absorb those long wave or those short wave infrared radiation. So infrared radiation just passes right through them and escapes to space. So this is the drought monitor I showed before. This is from October 2022. And we all know about the effects of the drought in the West. It's affecting crop growth. It's affecting water available for agriculture and for people to drink and wash. The droughts are also leading to fires that are hard to suppress. In fact, in 2020, we had $18 billion weather and climate disasters. They ranged from the western and central drought that we just talked about over on the left, to western wildfires, to 3 hurricanes that cost over $1 billion in damage, severe weather all across the country, tornado outbreaks, hailstorms, even in Texas, and cold waves such as we've just had in the Midwest and the East There was a severe one in December, late December of last year as well. So these climate disasters cost money. The 18 events in 2022 cost $165 billion worth of damage in infrastructure and housing damage and building damage, not counting effects on human health. Basically, this is the cost of repairing everything that was damaged in these severe weather events. And here's a graph we're going to take a little bit of time to look at. It looks terribly confusing, maybe a piece of art, abstract art, but it's not. It's based on real data collected on, you look at the left side, these are number of extreme events. On the bottom are years from 1980 to 2022. This is the period at which we've been tracking the cost of extreme events. Back in the early 80s, we had from 3 to 7 extreme events per year. These are the bars, and you can see what kind of events they were. The green parts of the bars are severe storm, numbers of severe storm events. So for example, in 1985, we had 1 severe storm. We had about 3 tropical cyclones. We had 1 major winter storm that cost over $1 billion, flooding that cost over $1 billion, but only a total of 7 major events. The costs are the red line for each year. So here's a red line. You can see the costs going up. Let's take a look at those costs. So across 1980 to 2022, the costs of these extreme events in 2022 dollars were almost $2.5 trillion, or $54.4 billion per year. In 2017, put a red star there, that was the record total cost thus far in this time period, 1980 to 2022, that was $340 billion with 16 events, most of which were severe storms. The red line is the dollar cost for that year, the cost estimate. The gray area around it is the uncertainty in that cost. When the events are high and costly, the uncertainty of that cost is high. And when they're low, we can pretty much estimate them with very narrow bounds. The black line is the 5-year moving average. So at any point on the black line is 5 years of cost. You can see the 5-year moving average in 2021 was a lot higher than the 5-year moving average in 2022 because 2017 dropped out in the 5-year calculation in this past year. The average cost from 1980 to 84 was $16 billion per year approximately. And the most recent 5 years was almost $120 billion per year. So you can see we've been ramping up in the costs of these extreme events. They're more severe and more frequent. The total cost last year was 18 events was $165 billion. That's the red star here. So we have a problem. It's costing us money. It's also costing us health. I want to now go back to the Earth. This is an artist's rendition of the polar ice cap, probably in about September. And the polar ice cap is actually a thermostat control on the Earth. How are we doing? Okay. My friend and colleague Henry Pollack, who's written a wonderful book called A World Without Ice, says in that book that ice doesn't have a point of view. It doesn't vote. It just melts when the temperature passes 0 degrees C. There's nothing we can do to stop it. When it warms past 32 degrees Fahrenheit or 0 degrees C, it melts. Why does that matter? Well, sea ice and ice on the ground have high albedo. What's albedo? Maybe you remember from 7th or 8th grade science or other science courses. Albedo is the reflection of shortwave radiation back to the atmosphere. And sea ice reflects about 30 to 45% of solar radiation, shortwave radiation, back to the atmosphere so that it doesn't have a chance to heat the Earth. Snow on land reflects 40 to 95%, depending on how much soot is on it, how rough it is. It can reflect almost 100% of solar radiation, but anywhere from 40 to 95. Whereas water reflects only 3 to 10% of solar radiation. And actually, most of the heat that is captured by the Earth is captured in seawater and then transferred to the atmosphere. So albedo matters, and this is data from the National Snow and Ice Data Center using satellite data. The red or the magenta line around here is the 1981 to 2010 median for September sea ice on September 15th. This is satellite-derived data. In September 2022, ice averaged about 1.9 million square miles. This is the 11th lowest ice cover in the satellite record. It's about 595,000 square miles below the 81 to 2020 record. So you can see the difference here. The difference in the area, which is now blue in September, is about 10 times Michigan's land area. So it's a huge amount of land. Michigan is about 60,000 square miles. The ice gone in September was 10 times Michigan's. In the last 15 years, we've had the lowest September extents in the satellite record. And this is the satellite record. Millions of kilometers. Since 1979, the September ice has lost almost 3.6 million square kilometers, 1.4 million square miles of ice, about twice the size of Alaska. One of the things I've done research on is the Arctic. And the Arctic stores billions of tons of carbon in frozen ground, frozen permafrost, which is organic rich. This is the area, all the colored area is the area of permafrost that now exists. The red area will be permafrost that's thawed by 2050. Orange area is assuming business as usual and the climate continues to warm from our emissions. Permafrost thawed by 2100, and areas still frozen by 2100 are about half of what the areas frozen now. How does permafrost work? Well, there's an active layer of permafrost which can be anywhere from 6 inches to a couple feet deep, which thaws in the summer. Grasses and shrubs grow on it. Decay is slowed, so it accumulates a thick organic layer, kind of like your compost pile. Gradually that gets buried and frozen in permafrost with ice wedges from runoff that freeze in the winter. But permafrost is melting. This is the Arctic Ocean off the coast of Alaska. This is in the foothills of the Brooks Range, where permafrost is just collapsing and water is running off, melting down. Scientists who study methane emissions from this water and this melting permafrost come up with huge numbers of methane that's now being injected into the atmosphere and warming the Earth. That's one example of a feedback. As the temperature increases in these wetland peats, both in the Arctic and other places, temperature rises. It increases warming of the peat. The peats thaw and emit more carbon dioxide, and more carbon is methane, and actually more nitrous oxide. So this is a feedback cycle that we need to take into account as well. One of the things that we haven't talked enough about as a scientific community is the effects of climate change on human health. And my colleague, Jonathan Patz, who's also on the Science Council and chairs our Science Council at the Environmental Law and Policy Center, was the lead author of an article in the Proceedings of the National Academy of Science that spoke just to this issue. Climate change from greenhouse gas emissions leads to regional changes in temperature, heat waves, precipitation, storms and floods. We haven't talked about aerosols and particulates, but as the climate warms, there's more opportunity for smoke and exhaust and particulates from fires burning to form aerosols. Pollen increases because of temperature and growing season length. And these have health effects. Temperature and heat waves drive heat-related illnesses and deaths, as do extreme weather events. But also the air pollution, the toxins, the mercury and cadmium that are released from coal-burning plants, contamination pathways, mercury that moves through fish, and heavy metals that are in plants and animals we eat from emissions, contribute to air pollution-related health effects, water and foodborne diseases, and also expansion of the ranges of vectors like ticks and malaria-causing mosquitoes, increased diseases. So there are really severe health effects. People who suffer from asthma have a high morbidity and high mortality if they live in the vicinity of a coal-burning plant or if there's a lot of diesel exhaust in their neighborhood. This is the IPCC special report on 1.5 degrees Celsius increase, and this looks complicated, but I want to just walk through it for a bit. The green line is 1.5 degrees increase in global temperature. The purple line is 2 degrees. We can look at heat morbidity and mortality over on the right-hand side. The scale here shows at current levels, actually I should say past current levels, 2006 to 2015. That's where we were, somewhere between 0.8 and 1 degree Celsius increase above pre-industrial. We were just starting to feel moderate effects of increased heat on human morbidity and mortality with a high degree of confidence. That's what this little H means. It means scientists have a high degree of confidence in that. As temperatures exceed 1.5 degrees, we move into an area where we have a higher incidence of mortality and morbidity. And if we exceed 2 degrees, we're in a danger zone. Really a lot of human effects on health. Crop yields, again, we're experiencing reduced crop yields because of warm temperature. And if we exceed 1 degree, 1.5 degrees or 2 degrees, crop yields will decrease. And guess what drives inflation? Food prices. Flooding, similar patterns. Coastal flooding, that's ocean coastal. We have different drivers for Great Lakes and inland lake coastals. But the list goes on. Exceeding 1.5 degrees Fahrenheit basically damages humans and the natural systems that support our economy and well-being. Now I want to talk about Michigan. This is the Addicks Reservoir after Hurricane Harvey hit Houston in 2017. Well, why am I talking about Houston in Texas when we're interested in Michigan? Hurricane Harvey was a Category 4 storm, made landfall in 2017. It damaged over 200,000 houses. It forced almost 40,000 people out of their homes into shelters. It affected 13 million people from Texas through Louisiana, Mississippi, Tennessee, Kentucky with severe weather. It was responsible for 88 deaths at least, and it caused $125 billion in damages. Remember that record year of 2017? Well, this single hurricane basically was responsible for half of the damage in terms of dollars and cents that year. It was second only to Hurricane Katrina in 2005, which caused $215 billion worth of damage. That's 2022 dollars. So why does that matter? I just read a book called Nomad Century by Guy Vince that was recommended to me by a friend from Kalamazoo who's in the Kalamazoo Climate Coalition. It's called Nomad Century, How Climate Migration Will Reshape Our World. If we look at Michigan, and particularly northern Michigan in the summer, we're seeing build out and development and more people moving to the north. It could be just the tip of the iceberg, so to speak, of migration to northern Michigan, climate refugees, people who are moving away from the fires in the West, the smoke in the West, the droughts in the West, severe climate in other parts of the country. In northern Michigan, we're fortunate. We are having impacts, but they're not as severe yet as impacts in other parts of the country. We can anticipate more year-round residents, especially as many types of work become possible to do remotely. Migration across the U.S. border much of it's driven by climate change. People who can no longer subsistence farm in Central American countries or other subtropical and tropical countries because of severe weather. So this is something we're going to have to plan for. And again, this requires conscious thought and work of all of us, and also conservation organizations like Tip of the Mitt Watershed Council, like our land conservancies, like our universities and our communities, to build communities that are sustainable, that protect our natural resource, that protect the natural systems that provide for us. The Environmental Law and Policy Center just developed a report on rising waters. What we're having in the Great Lakes isn't consistent a rise like the sea level rise, but rather we're having more variable years, and we're having higher variations in water levels from high to low over short periods of time. This is causing problems. Climate change in our region is fueling these highs and lows. We've already experienced 1.5 degree, or almost 1.5 degrees rise in annual mean temperatures, and a 10% increase in annual precipitation over the past 100 years. And about 35% more rainfall is falling in the 4 wettest days of the year, but larger than that, we're getting more and more of our rain as storms and less of it as gentle rains. And we're getting more and more of that rain in the wintertime. Part of the reason for this is for every degree of warming, the atmosphere can hold more water vapor. And as that water vapor comes off of the Great Plains and the lakes and moves to the upper atmosphere and cools, that water vapor comes down as storms. So we're having more frequent and intense rain and snowstorms. They're contributing to flooding in our region, especially in combination with high lake levels. And these stronger winds and heavier storms are leading to erosion, beach loss, damage to residential areas, infrastructure along the Great Lakes shorelines. But those same events are playing out on our inland lakes as well. One of the things that we're experiencing more and more is rain on snow events. And I understand you just had one. I was up north Monday and I came home Monday night, and you're having rain and snow events. Well, these rain and snow events move water directly into streams. It doesn't have a chance to percolate into the soil. It removes nutrients, fertilizers, sends them down the stream, sends them into the lake, and increases pollution events as well as flooding events. These are serious things. And when that water falls in the early spring, in the winter, in the late fall, it is moving nutrients out of farm systems, out of agriculture systems. It's moving pollutants off of our streets that don't have, that aren't intercepted by the natural systems that have roots and capture those nutrients and put them back into biomass and put them into soil. Rather, it's going out into the lake to feed toxic algal blooms. So what can we expect in the Great Lakes? Precipitation will likely increase flooding across the region. Higher summer and fall air temperatures will increase evaporation during the growing season. We do have droughts. And so coupled with summer precipitation that's increasingly variable and sometimes comes down in big storm events, moves nutrients and moves sediments into the rivers and lakes. By the end of the century, if we can't do something to lower emissions and move the climate back into a more stable state, we can expect more of this. Agricultural watersheds I've talked about. We basically move more nutrients and sediments into our lakes and rivers. That not only damages the lakes and rivers, but it leads to crop losses. Summertime higher temperatures in our urban areas will cause poorer air quality. And, you know, that air quality can be detected by towers at the biological station coming up from Chicago and Detroit. The most vulnerable people will be affected, people with asthma and elderly. These extreme events, of course, we've already talked about this. They basically exacerbate flooding. And that water with extra nutrients can affect our drinking water as well, and affect our infrastructure that's built to capture drinking water. So limiting of warming to 1.5 degrees requires immediate transformation. These must be made across energy, land, industrial, and urban other systems. We need to develop new technologies, and we need to basically consider our geographies and our landscapes and manage them for sustainability and resilience. Climate change over 1.5 degree warming will hit and impact the most vulnerable communities. Risks associated with warming are lower at 1.5 degrees, and frankly, we're not gonna get out of a world that isn't 1.5 degrees warmer. But 1.5 degrees is much better than 2 degrees C. Emissions will need to reach net zero by 2050 for us to achieve these goals of limiting warming below 1.5 degrees. And everybody will need to strengthen their action without delay. Cities, counties, private sectors, individuals. Individuals can't do it alone. We need policies, and we need an electrified grid. We're not on track to limit temperature rise to 1.5 degrees. This was our emissions, 52 gigatons of CO2 equivalent. By 2030, we're headed here. That's only 7 years from now, but we need to be here in 2030 to be consistent with 1.5 degree limiting temperature to 1.5 degrees. And we need to be at net zero by 2050. So there's a small window to avoid the worst case scenarios. We'll need to cut greenhouse gas emissions, make our communities more resilient. We are advancing technologically. The technology is here to reduce emissions to net zero by mid-century. Companies are doing this. Our utilities, our electricity utilities are investing in clean energy, even while Washington moves slowly on climate change regulations. Cities and states and institutions are acting. So we need system-wide changes and incentives to reduce and eliminate carbon-based energy. And it's now time for comments and questions. So thank you all. I appreciate you participating in this, and I'm sorry I wasn't able to entertain questions during, but I think we can go to the chat.
Actually, we're gonna go to the Q&A, and I'll try to summarize some of these questions, so some of them are a little bit longer than others. There was a question asking if you could discuss food waste in landfills and how that's creating enormous amounts of methane, and the need for more communities to address food waste.
Well, that's a great question. Thank you. You know, food waste is amazing. It's basically, food is carbon, it's sugar, it's fats, carbohydrates, and protein, and oils. And it's a tremendous resource. Putting it in dumps where it's buried by plastic and paper and it decomposes does the same thing that melting permafrost does. It decomposes under low oxygen conditions, which produce methane. High oxygen decomposition produces CO2, and that's a troublesome enough greenhouse gas, but methane is far more powerful. And the food you throw away, and our friend in the Emmett County recycling position talks about there is no away. You don't throw food away, it goes somewhere, and it doesn't disappear until it becomes methane and CO2 in the atmosphere. So I think we need individuals who don't have trash pickup can compost their food waste. I do that, we do that, many of my friends do that, and many of you do that. And it's amazing to see that compost work. It's really fun. It's an educational opportunity for all of us. And it produces a valuable compost that we can put on our gardens and release those nutrients to plant growth. The plants will take the nutrient up and they'll also remove CO2 from the atmosphere that was put into the atmosphere by the decomposing compost. So I think we need municipal composting, and I know some municipalities have it, but we also need individuals to compost their own food waste before it goes into the community compost or trash truck. I hope I answered that question.
Thank you. And so we have another, it's just kind of restating, when you talked about the IPCC, it says, basically then IPCC performs meta-analysis only. Is that correct?
Yes, that's true. Scientists who participate in the IPCC reports do their own research, but that is not part, excuse me. The IPCC really takes a big view and assembles a lot of data and quantitatively identifies trends.
So there's another question asking you, were the dollar amounts associated with extreme events adjusted to account for annual inflation?
Yes, they were all in 2022 dollars. That's a great question. The other thing is those dollar amounts do not include the costs of human health, of medical care that's needed, of long-term chronic effects, not only on physical health, but on mental health. The article in the Texas Tribune and in the New York Times that I got the data from on the Hurricane Harvey displacement, there are a lot of people who have had multiple, through the past decades, damages to their house from these hurricanes and severe storms, and it basically has mental health effects. It has financial effects that translate into mental health effects that are not good.
Thank you. And so how much of the increased cost is related to building in high areas or building in areas of high risk?
That is an excellent question. A lot of it is. And that's what early on in the talk I said we need to play defense now as much as offense. Offense is cutting emission. Defense is trying to build more resilient communities and infrastructure. And in some places we are developing policies, zoning and other, to prevent building in high risk areas. Excuse me, I've been talking too long. But yeah, a lot of the damage is in high risk areas, low lying areas, frankly, and a lot of that damage is in where poorer communities are located because the land is cheaper.
So there's a couple of questions related to the data before the human impact, and asking if there were any explanations for the rapid rise of CO2 before human impact.
CO2 was relatively stable before the industrial age, which really started in England in the mid 1800s, early 1800s. But there was oscillation, and it's complex. It has to do with ice cover, which, when the glaciers advance, it covers up land that's either vegetated, that's absorbing and re-emitting CO2. So when the ice cover advances, CO2 in the atmosphere can go down for many reasons, but partly because it's colder and decomposition and release of CO2 from decomposing organic matter decreases. At the same time, uptake decreases, but by and large, you see when in the interglacials, the CO2 is going down. When the ice retreats and the CO2 starts getting released, there's sort of a positive feedback that brings the CO2 level back up to 280 or so. So, and I will say, you know, we really, our younger generations and generations to come can blame me because those gases, and they can blame all of us who are my age, really started being emitted in mega quantities about 1950, when we really started ramping up industrial agriculture. We really started building a transportation network that was built on cars and trucks, and manufacturing, you know, basically unregulated manufacturing, unregulated emissions starting in the 50s. We're just now starting to bring them down. So we could see effects of the Industrial Revolution from the Civil War in the US forward, but it really ramped up after World War II and the prosperity that the West in general, the Western world, experienced.
So there's a comment and a question about a lot of the problems being related to bad planning and bad policies, such as the Wetland Mitigation Program. And so it's kind of a rhetorical question. Why would anyone think it would make a difference to fill in 20 acres in one end of the state to allow someone to buy credits to purchase some arbitrary wetlands 300 miles away?
I think that's a really important question and a very good one. And I can't answer it. I don't think it makes any sense. I mean, yes, yeah, because the wetland that was filled in was functioning within a context of inputs, from upstream and local geography, geomorphology, and to put one in another place might restore some of those functions, but it would take a long time, and it might not be in the right place anyway. It might be, So yeah, great question. We need people working on that, and there are people working on that. So some of the Tip of the Mitt Watershed members and friends are working on that question. So thank you for that.
Next question. Are we seeing an increase in the number of sudden stratospheric warming events in line with rising global temperatures? And if so, what effect might these have on northern Michigan and the Great Lakes?
Oh man, that's a great question. I want to, whoops. This leads to the polar vortex. So the warm air that is warming for reasons we talked about. So let's go to the left side of this. Is everybody still got am I sharing my screen?
Yes.
So the stable polar vortex is way up in the stratosphere, 10 to 30 miles above the surface. It's underlain by the jet stream. When warm air moves north, it can disrupt the polar vortex and basically split it in two or cause it to move, sometimes even in a different direction, but it disrupts it. And what that does is it moves the polar jet stream into a wavy formation that freezes some places and heats other places up where it doesn't dip down. So last week when New England had sub-zero temperatures, we in Michigan and at least southern Michigan had 40s temperatures because we were in one of these sort of places where warm air was intruding, and we were just west of where the south air was moving down. Now, the polar vortex is not well understood, or the disruption in the polar vortex, and we haven't been monitoring it for very long. So there's nothing definitively we can say about global, warming of the atmosphere in general driving disrupted polar vortices, but it's an open research question, and it certainly is a possibility or probability that warmer air in the south can have effects of destabilizing the colder air in the polar regions. I shouldn't say the north, because that can happen in the south too. So I sort of went off on a sidetrack, but the idea is that this is part of what drives this freeze, thaw, and rain on snow events, is events like a polar vortex. And just warming in general does that, right? Because weather is inherently variable. So if you have a warmer winter, and our winters in Michigan, northern Michigan especially, are warming more rapidly than our summers. So if you break it out by seasons, we're having warmer winters, and with or without a polar vortex, we're having more rain on snow events and more freeze thaw events in the winter. I hope that answered the question, but if it didn't, I'll be happy to follow up.
We have quite a few additional questions. And so at this point, because we've reached that magic hour, we will wrap up our session, but also follow up with those who have asked additional questions and try to get those answers to you. And then when we post this online, we'll try to share those answers as well for those who are curious about those answers. So thank you so much, Knute, for an excellent discussion here on the emerging impacts of climate change, both in our planet, but also here in the Great Lakes area. You've generated a lot of interest, and so we'll have to pull up quite a few different questions here, and we'll follow up.
Well, thank you, Katie, and thank you all for your participation. I'll do my best to answer questions. And I'll be happy to spend some time on that, because I always learn from people's questions, and that's the whole idea of being a person, isn't it? Is to continue learning. So please feel free to put those questions in the chat, and if I can't answer them, I'll be honest with you. I might lead you to someone who can.
Well, I think you're the right person to be able to do that. So we really appreciate you, the time you put into this presentation and with us today. So thank you so much. And for everybody who joined us today, thank you for this discussion. Obviously, there's a lot more that we can talk about on this topic. So at this point, I just hope everybody was able to participate in the poll, and encourage you to join us again in 2 weeks for the next topic that we have on our agenda. And we're really pleased with the participation that we've had today, as well as for the first 3 sessions. So thank you, everyone. I hope you have a great day. And again, thank you, Knute, for your excellent delivery today.
Thank you all. Thank you.